Okay, Pincast number 4, I think? Yeah, 4. We have two problems for this one. The first one's problem 2.35 from the book. It gives us that we are going to be finding work or energy using a method where we bring charges in from infinity over some dr value. Can't remember the exact wording of the problem, but something like that. So we need dq in terms of dr. So if we start with our regular equation for charge density, we have rho equals q over v. Since this is a uniformly charged sphere, we can just say this is q over 4/3 pi r cubed, and then q equals 4/3 pi r cubed rho. So then to get dq, we just take the derivative of this with respect. We'll take the derivative of this with respect to r. So we have the 4/3 pi rho. Derivative of r cubed is 3r squared, and then we have the dr term. So its total is 4 pi rho r squared. Yes, dr. Then if we're going to set v of infinity equal to 0. Then from equation 2.39 in the book, we have work equals q v of r, and dw or dwork equals v dq. Plugging in for dq, this gives us v 4 rho pi r squared dr, and v is a function of r as well. So this gives us the change in work as a function of change in r. So now we need to find v of r at the surface of the sphere, which has a radius of big R once we compact this snowball down. So if we look at this sphere, I'm going to draw it without the big R. We have our distance. We have this as our point of interest. This is R. We have some dq over here, distance r prime from the center, and then we have r script right here. And we know the potential is v of r equals 1 over 4 pi epsilon naught integral of rho r script d tau. R script is given by the law of cosines. We have our two sides, r squared plus r prime squared. And then from the law of cosines, we have the 2r prime cosine theta term, where theta is the angle between r and r prime. So, and then we also got d tau, which is the regular volume element for a spherical shell, r prime squared sine theta d phi dr prime. Alright, so now writing v out, you have v of r, pulling some constants out, rho over 4 pi epsilon naught, integral from 0 to r, integral from 0 to 2 pi, and the integral from 0 to pi, r prime squared sine theta d dr prime d phi, and then we have the r script in the bottom, r squared plus r prime squared minus 2r r prime cosine theta d dr prime. So we can make this a little bit simpler. We can do the d phi part. So that's just we're gonna have 2 pi from that. So 2 pi rho over 4 pi epsilon naught, integral from 0 to r, 0 to pi, r prime squared sine theta d dr prime over the square root of r squared plus r prime squared minus 2r r prime cosine theta. And then we have this really ugly integral that no one really ever wants to do. So I found this nice web page. It's called physicspages.org. They actually have this problem solved on there, but they also have this integral. So I took the integral part from there, and the integral turns out to be r squared over 3 minus r squared over r squared, since we're at the surface. So we have this part that goes to 1. So then that just gives us 2 pi rho over 4 pi epsilon naught. This is 3 minus 1, which is 2, so we have 2/3 r squared right here. So v at the surface, now plugging big R in for little r, is rho, or no, we're just going to leave it as little r for now, rho r squared over 3 epsilon naught, which is v of r at the surface. Then remember dw, we had the 4 rho pi r squared rho r squared over 3 epsilon naught, or this is the v part, dr, and that becomes 4 pi rho squared over 3 epsilon naught r to the 4th dr. Then we can integrate to find the work or energy. The integral from 0 to big R now. Now we're going to switch it over to big R. Everything except for the R is a constant, thank God. So this is going to give us 4 pi rho squared r to the 5th over 15 epsilon naught. Got that just from, doing the power rule. And so we get the 5 and then add in the denominator, and this becomes r to the 5th, and we plug in r. So then, if we remember that rho equals q over 4 pi r, no, 4/3 pi r cubed, we can plug that in for rho squared, which there's a lot of arithmetic here. We have 4 pi, squaring this, q squared over, there's 9 there, from this 3, that gives us 9. 4 squared is 16, pi squared, r to the 6th, times r to the 5th over 3 epsilon naught. Alright, now for a lot of cancellation. So r to the 5th cancels, leaving 1 r in the denominator. Pi and pi squared leaves 1 pi in the denominator. Get a 4 here, get a 3 in the numerator. So we have 3q squared, and then we have a 4, oh no, I apologize, this is 15, not 3, so this goes to 5. Anyway, so we have a 5 and a 4 in the denominator, so that's 20, and then pi epsilon naught r, and that is our total energy given using the snowball method. Second problem we had to do, number 6, which gives us we have a spherical shell, I think, because I can't remember exactly what the problem says. I'm going to say spherical shell and hope that's right. Once again, it has a radius of r. Yes, this is a spherical shell, now I remember. And it has a that's all that's given. Yeah, that's all we need for this. Anyway, so part A asks for the potential as a sum of Lagrange polynomials, which can be found in the book as v of r theta equals the sum from L equals 0 to infinity, some constant A sub L, R to the L plus some constant B sub L over R to the L plus 1, Lagrange polynomials, cosine theta. And that was just right from the book. They derive it in the book. I'm not going to derive it. It would take too much time. Part B, we're asked to find the potential inside this sphere. So inside the sphere, we have these. So we have these two terms: a sub L R to the L and b sub L over R to the L plus 1. As we go to 0, radius R equals 0, this term goes to 0. This term blows up to infinity. We cannot have an infinite potential. Thus, for inside the sphere, we do not have the b term. So now the new potential is v of r theta equals the sum from L equals 0 to infinity, a sub L R to the L, Lagrange polynomials. Huey, stop. All right. So now we are given. Oh yeah, the other thing we're given at the surface at r equals r. The potential is v naught cosine of 2 theta. So we're going to set this equal to the Lagrange polynomial part. A sub L R to the L, big R to the L, L cosine theta. And this is where we would usually do a Fourier's trick, but I'm actually going to manipulate this a little bit to get into a form where we don't have to. So v naught cosine of 2 theta equals, using some trig substitution from sosmath.org, cosine 2 theta is 2 cosine squared theta minus 1. So then we have 2. I'm going to get this in terms of Lagrange polynomials. So I'm going to do 2 times 4/3 times 3/4, which is just 1, so I can legally put that in there. 2 cosine squared theta minus 1. And then this gives okay. So we have 4/3 of 3/2 cosine squared theta. And if we pull 4/3 out of the 1 as well, that gives us 3. Okay, I'll just leave it as 1, so I don't confuse myself with what I have written down over here. So then recopying this down. Now we're going to express 1. We're going to have, so we have 4/3 minus 1/2. This right here is 2/3, so we need to have subtract another third out. Oh, I know that's what I'm doing. Okay, so then we have 4/3 cosine squared theta minus 1/2 minus 1/3. And so, and this minus 1/3 can also be written as minus 1/3 times 1. This part right here is Lagrange polynomial, the second Lagrange polynomial, and, or P2. This part is P naught. So then this is V naught 4/3 P2 cosine theta minus 1/3 P naught cosine theta, which is still equal to the sum of L equals 0 to infinity a sub L r to the L p sub L cosine theta. So we only keep two terms, the L equals 0 and the L equals 2 term. And for the L equals 2 term, we have V naught times 4/3 equals A2 R squared. So A2 is V naught, 4V naught over 3 R squared. And for the 0 term, we have V naught times 1/3 negative V naught times 1/3 equals A naught R to the 0th. So A naught is just negative V naught over 3. All the other constants go to 0. So with those being R2, then we can write V of R comma theta. Without the sum, we have A naught, which is negative V naught over 3, times R to the 0th power, which is just 1. And then the Lagrange polynomial. And then we have the second term, which has the A2 value, 4V naught over 3 big R squared, times little r squared, P2 cosine theta. And if we plug big R back in, nothing changes here. And then the R squareds would cancel, just like... Sorry. Which would be exactly what we started with. Alright, so that is that. And then the last part asks us to find sigma as a function of theta. So for this, since this is a spherical shell, it has no charge inside. It's all on the surface, just like a conductor. Thus, the induced charge will operate like a conductor. And the induced charge, given an equation 2.49 in Griffiths, is negative epsilon naught partial v with respect to n. Since n is radially outward, it's negative epsilon naught partial v with respect to r. So if we do that, we have negative epsilon naught, and we're going to take this v term and take the derivative of it with respect to r. This first part is a constant, so we drop it because it goes to 0. And if we take the derivative of the second part with respect to r, we get 8/3 v naught over r squared little r p2 cosine theta. So if we clean it up a little bit better, sigma theta. Oh, and we evaluate this at r equals r. So then sigma theta equals negative epsilon naught times 8 v naught over 3 big R. And then the second Lagrange polynomials. And that is our sigma. That is our induced charge. Charge density. Okay.